Hello, everyone. Thank you so much for coming. Today, we're going to be presenting our Thesis 2 final presentation on our computer vision parking management system. I'm Mariam Taha, and with me is Mazen Hassan, Zeyad, Usama, and Ahmed Shalaby. And this project was supervised by Dr. Mohamed Sedky. So first of all, I'm going to be taking you throughout our agenda for today, starting off with our motivation, and then our thesis objectives, our architectural model, our feature set, the models that we have implemented, our mobile application and admin panel, and finally our empowerment outcome. So starting off with our motivation, who here has not faced issues while finding parking on a near daily basis? So during our research, we found that an average American spends 17 hours looking for parking, $345 on wasted gas, and 42% of them miss appointments due to not finding parking. So this took us to our project aim, which was to develop a smart, user-friendly, and cost-effective system for parking management and to create a commercial-ready car park management solution. At the beginning of the year, we set thesis objectives that we aim to implement throughout our thesis. Starting off with gathering our project requirements and then followed by researching and developing our empty spot detection model in terms of camera calibration and object detection, followed by researching and developing our license plate detection both for English and Arabic license plates. Moving on to designing our mobile applications in terms of authentication, parking availability, navigation assistance, user differentiation, and reporting violations. Followed by our designing our admin panel in terms of authentication, calibration, parking monitoring, and report reading. And then our system integration and system testing. And finally, our commercialization strategy in terms of our business plan, pricing model, and business website. So my colleague Mazen will be taking us through our architectural model.
Okay, moving on to the architectural model to get a big picture of how our system works. So if we start here from the leftmost side of the diagram, we can see that we start with two types of footage. The first type is the parking lot footage, and the second type is the entrance camera footage. Going from there, both of these types of footages get sent to a set of hosted APIs that perform actions such as frame capture, sending the data for the parking status so that we can see which spaces are available or not, our automatic number plate recognition, as well as sending our annotation data between RoboFlow, our database, and our user endpoints. If we go to our database, we can see here that we use Firestore, storage, and authentication. And we use these features in order to transmit the needed data from our APIs and RoboFlow into our user endpoints, which are both our admin panel and our mobile application. If we look to the top of the diagram on our admin panel, we can see that it receives information such as parking status. It sends data such as annotation data, which will be used in calibration, as we'll explain. We retrieve violation reports, as well as retrieve the status of the occupants in our parking lot. If you look to our mobile app as well, we see a very similar style of data. However, we also send the user location from the mobile application to our database to facilitate our navigation features. We also receive our user reports. We send and receive from the mobile application. We receive our users' information from our database, as well as the parking status of the parking lot to give an abstract representation to the user of the available parking status.
So in order to create a comprehensive and cohesive system, these are the features that we have came up with. Starting off with our parking spot status detection to be able to detect at any given time point whether a spot is available or occupied. Moving on to our navigation to parking lot location after user has chosen their desired parking spot. Followed by our number plate detection, and this is used to detect the entry and exit times and can be used to implement a ticketing system. Followed by users' ability to self-identify either as users with disabilities or users with electric vehicles, where our system then guides them to specialized parking spots. Followed by our parking violation detection, which is done through three main methods. Firstly, automatic detection of cars parked in non-parking spots. Secondly, is detection of cars parked in undesignated areas through our automatic number plate recognition. And lastly, our user reporting of parking violations through the mobile application.
Okay, and now we are going to talk about our models. So in our effort to enhance our model's accuracy and performance, we use the state-of-art transfer learning technology. This way helped us to enhance the performance and the accuracy of our model. And in order to achieve that, we firstly started by training our models, YOLO V3 and RoboFlow on the PK lot dataset, which includes more than 12,000 photos of different parking lots taken from different angles and perspectives. After that, whenever we are going to implement our system in a new place, we are going to ask them to provide us with real footage from their cameras in order to apply transfer learning on. And as you can see, this is the difference between the output before and after applying transfer learning. And in order to achieve a comprehensive solution, our model is capable of detecting cars that are parked within unauthorized area and report this to the admin panel. And after a specific time frame, the admin panel flags this car as a violated one.
All right, so for our second approach for developing the empty spot detection model, we decided to make use of the already existing YOLO V4 object detection model, and we decided to further train this model in order to achieve better results. So we further trained this model on the existing dataset, which is the PK lot dataset. This dataset consisted of a training portion, which consisted of 6,929 images, with a corresponding validation dataset, which consisted of 1,980 images. And we were able to achieve a maximum mean average precision of 97.91%. And basically, we developed this model again through a second approach because we have an admin panel component in our system. And we found when developing and testing the system, we found the calibration feature that is integrated in the admin panel component was not efficient enough when it came to using the model that was developed through the first approach. But however, upon the model that was developed through the second approach, we found much better results. And to be more specific, the first approach of the model it required between 400 to 600 images when it came to the calibration feature, which is basically applying transfer learning on the model. However, with this second approach, the number of images required were decreased to a range between 30 to 50 images. So this basically sums up the empty spot detection model, and here's a sample result of the second approach, on identifying both the space occupied and the empty spaces within a given parking lot. So now we move on to the automatic number plate recognition model. So basically, this model is divided into two parts. The first part, which is the empty spot, which is the number plate detection, and the second part is the OCR extraction process. So let me start off first with the empty spot detection part. My bad, the number plate detection part. So for the number plate detection, we also had two approaches. The first one was using a famous edge detection algorithm known as the CANI algorithm. It's a famous algorithm in the image processing. So basically, by using this algorithm, we were aiming to find the number plate within a given image through detecting the corresponding edges for a number plate within a given image. And this is done through applying a set of pre-processing image techniques such as grayscaling and blurring a given image. However, upon developing and testing this algorithm, we found that the results yielded a very low accuracy, which led us to our second approach, which is to train our own model. This approach, again, is similar to the second approach which we used in the empty spot detection model. So again, we made use of the YOLO V4 object detection model, but this time we used a different data set for the number plates. And the data set was Google's Open Images data set. It consisted of a training data set of 1,500 images with a corresponding validation data set of 300 images. And at different levels of iterations, we were able to reach a maximum mean average precision of 87.7%. However, we had a second trial in order to improve this mean average precision, where we retrained the model again, but this time on a larger data set, which consisted of 5,500 images for the training data set, with a corresponding 1,100 images for the validation. And we were successful in that we were able to reach a higher mean average precision, which was 90.32%. Here are some of the test results for the number plate recognition. You can see that the corresponding bounding box with the confidence levels are presented in the output images. Now my colleague Mariam will take us through the OCR extraction process.
So for the second part of the automatic number plate recognition, which is the optical character recognition, we tested different models starting off with the Tesseract OCR, but we found that the Tesseract OCR works best for clean images without noise, and it needs images to be in a set layout for the best accuracy, which is not available with our system. So we moved on to the Sokhra OCR, but we found that it only works with images taken from a frontal view and has low accuracy when handling images taken from different angles. So this led us to Easy OCR, which is the model that we ended up using, because we found that it was able to detect text with different layouts and backgrounds from different angles. So in an effort to improve the accuracy of the Easy OCR model, we took the image through a few pre-processing steps before passing it to the model, starting off with grayscaling and blurring, then thresholding, dilation, rectangular contour, detection, and finally copying and reading the letters individually. However, we found that for the English model, it actually worked better without image pre-processing, with the model without image pre-processing having an accuracy of 99.8%, while the model with image pre-processing had an accuracy of 95.6%, and this was tested using the PKU dataset. However, for the Arabic detection, images without image pre-processing had an accuracy of 73.3%, while images with pre-processing had an accuracy of 82.1%, and this was tested using the EALPR plates dataset. So this is an example of the algorithm working on English license plates and Arabic license plates, and we find that it was able to detect the numbers and the letters correctly. Moving on, because of our system not having set camera locations, we tried testing it using different camera angles and using different lightings, and we found that it was able to detect the number plates correctly, both using different angles and different lightings. And my colleague Zeyad will be discussing our mobile application.
So now we'll be proceeding with the mobile application component of our management system. Let me first just mention that this component is critical since it is fully responsible for handling the end user experience. So for the mobile app, we developed it using the React Native framework, and we use Firebase as the backend. Using React Native means the app is both deployable on iOS and Android devices. And to demonstrate the user experience, we'll go through a demo of how the app works. But before going into the demo, let me just briefly mention the main features of the app. So the app consists of the following features, which are authentication, parking availability, navigation assistance, user differentiation, and being able to report violations to the app. So for the first feature, in order for any given user to utilize our app, they have to sign up onto the app or directly log in if they do have an account. And basically, in this case, we can see that a user called Mohamed, in this case, has to fill in the required fields, such as the email, password, the username, and the license plate number of their vehicle, because it will be used as part of the number plate recognition model that we had mentioned earlier. And they also have to indicate whether they have a disability or whether they use an electric vehicle to commute to the parking premises, because this data will be used in the user differentiation feature, which will shortly be explained. So, and the authentication that we use the Firebase authentication service. But basically, after the user successfully registers onto the app, they are presented with three main tabs. One of them is the parking availability tab. Basically, this tab represents an abstract representation for a given parking lot. And from there, the user can select a parking spot, an empty parking spot for which they can receive navigation assistance. And when they select a spot, they are navigated to the navigation screen that we can see on the screen there. So basically, we made use of Google Maps API, and from there, the user can receive the shortest path possible towards that spot with the corresponding distance and duration values. So now moving on to the user differentiation feature. So we had seen earlier in the authentication part that Mohamed had registered as a user that does not have a disability, but he commutes using an electric vehicle. And from there, we can see that there's an empty parking spot that is dedicated to users with a disability. However, when he tries to access this spot and receive navigation assistance, the app prevents him from receiving this assistance because it is dedicated only to users that have a disability, which is not in Mohammed's case. And the same goes to users that, for example, do not own electric vehicles but try to receive navigation assistance to electric vehicle spots, for example. And it goes without saying that if navigation assistance is not provided to if user tries to select already occupied spots. And for the final feature of the report violation, you can see that this feature basically allows a given user to report any violations that they observe within a given parking premises. And basically, they do that through filling in the required fields, which are the license plate number of the vehicle committing the violation. They also select a description of the type of violation that is taking place. And finally, they attach an image, which is somewhat of a proof of the violation that is taking place. And we can see that in this brief demo. And simply with a simple click of a button, the report is sent to the admin and the corresponding actions can take place. And one important thing to note here is that the corresponding longitude and latitude coordinates are attached to the report, which are sent to the admin, and the admin can retrieve this data, and thus he can be able to precisely locate the location of where the violation is taking place.
I will now be discussing the other type of user endpoint we have, which is the admin panel. So first, to briefly go over the features before we go into the demo of the admin panel, we have four main features, which is user authentication, the calibration feature, the parking monitoring feature, and the report reading feature. And throughout this demo, we'll see how this user endpoint interacts with other user endpoints, such as the mobile app Zeyad just discussed. So let's start with the first screen. Admins will be prompted to log in, and they will be authenticated through Firebase, where they will then receive a success welcome back message if they are found to be the correct user. From there, the admin will be presented with the main screen, and we will go through each of these tabs now through the demo. First of all, let's go through the calibration panel. The main use of the calibration panel is in regards to if issues occur with the viewing angle from the camera. We found that our empty spot detection model would have very low accuracy. So in order to facilitate any of these issues happening, we created a calibration tool. The user will be prompted and a set of images will be uploaded. This is a sample image from the parking footage. And then they will be prompted to annotate onto the image what they perceive to be the empty spots. As we'll see here, the user goes and marks onto the annotation panel here. And then from there, that data is sent to the model, where we apply transfer learning techniques to enhance the performance in case of anything that might go wrong. This is the format of the data we sent to our model, which is in the YOLO v4 darknet format, which includes the annotated image, as well as its corresponding bounding box and its class type. And from there, our model recalibrates in order to have a higher accuracy. Moving on from here, we will go to the parking representation feature. If we look here, the car at the bottom left just left, and as our UI reloads, we will see that on the bottom left of the screen, as soon as it reloads, we'll see that the spot is now available to look in. And for another example, we'll see the car in the center, the blue car here will move shortly, and the UI will reload, and we will see an update in our UI as well. They got into the car. Okay. And as they start to leave and our UI reloads and regenerates the map from our back end, we will see that the corresponding spot will also be empty here, as we can see here. Okay, moving on from there, another part of our tabs is seeing who is currently parked in our parking lot. And this feature works in conjunction with the license plate reading model we have. And from a test video we've uploaded, we here have a bunch of license plates as well as their entrance times. And we can filter them by date in order to see who entered the parking lot when and act accordingly in the case of any extraneous activities happened in the parking lot. We have this information as a security feature. Moving on from there, let's see how the report reading functionality works with the mobile application. So here our admin will be at their homepage. They'll decide, I want to see what kind of reports have been here. We go here to our report reading panel, and we have five main tabs, which are our report ID, our description, the license plate, the image, and the location. And when we open the image here, we will find that, yes, this is the person that parked across 3 parking spots. This is me parking here for the purposes of testing. And it has been correctly sent to the admin with the location, and the admin can handle the report accordingly. Okay, moving on from there, my colleague Mariam will be discussing our empowerment outcome and how we hope to achieve it.
So our empowerment outcome was to come up with a commercialized product. So what we first did was we analyzed the existing solutions on the market currently. We found that existing solutions cost $250 to $800 as a setup cost per parking spot, and it costs $10 per parking per month as a monthly fee paid on average. And then for our market analysis, we found the 2 main competitors for our system: Intercomp, which is a sensor-based solution, and Parkleo, which is a computer vision-based solution. All of them perform parking status detection. However, Parkleo did not have a user mobile application, while Intercomp was obviously not a computer vision solution. Neither of them were budget-friendly. And Intercomp did not have real-time video monitoring as it only used sensors. And it also did not have easy worldwide deployment also because it used sensors. So our system was the only one that was able to achieve all of these functionalities. And we divided our business expenses into 6 different criteria. The first one was the Firebase Firestore, and then RoboFlow, Google Cloud's GCP and the API services, and then deployment both on the App Store and the Play Store. Using these numbers, it helps us set our own prices, and we divided our prices into 3 main categories. First one was the consultation fee, which is a one-time cost of assessing the parking space and recommending camera locations, and it is $1,000. The second is a setup fee, also a one-time cost to run the system and determine the parking locations, and it's $5,000. And then our third is divided into our monthly payments, and these vary per parking size, determined by the features added. So our tiers are as follows. We have 4 payment tiers. The first one is the basic tier, and it only includes the admin dashboard and the basic mobile application. It costs $4 per parking spot per month. Moving on to our pro tier, it has added on to the basic features, violation reporting and special parking assistance, and it costs $4.5 per parking spot per month. Moving on to premium, that has added on to the previous features, license plate detection. It costs $5 per parking spot per month. And finally, for VIP, this is includes all the full features as well as payment management, and it also costs $5 per parking spot. However, it also takes 20% of all fees that users pay through the system. So we created a business website for potential clients to be able to learn what parkour is. We also added a quote estimate in the system where they'd be able to input the number of parking spots that they have, and they'd be able to get a quote based on the 4 different tiers that we have. And we also have a contact us section that is also linked to Firestore, where they can leave their information and someone will contact them. So for our predicted profits for the first year, we aim to launch it for 1 client with a revenue of $24,000, a cost of $13,000, and expected profit of $11,000. By year 3, we aim to grow to 10 clients with a revenue of $240,000, a cost of $95,000, and a profit of $145,000. And by year 5, we aim to sell our company for a profit of $1 million. Reiterating on Parkour's unique selling points, the first is that it is a holistic system that merges all parking system aspects that a company might need, including our automatic violation detection, our parking monitoring, and our ticketing support. And it also has minimal on-ground deployment, which allows our system to be priced considerably lower than the average market price. This concludes our thesis project. Thank you so much.